So climate change is a topic that has been percolating in the wider consciousness for a long time. There have been articles published in various publications, even like New York Times. I think that I go back almost a decade. Uh, the topic has definitely been in the consciousness since the 60s, uh, definitely the 80s, because there are videos of Carl Sagan and Isaac Asimov talking about this disastrous path that we're on for when it comes to burning fossil fuel and how that's altering the climate. Now, there seems to be a lot of evidence to posit that there is a correlation. All of that being said, I'm not a climate scientist, so I haven't looked at the data, and if I looked at the data, I'm not a statistician, so I wouldn't know how to make sense out of that data set. So I must make that I must make that be known, because I don't want to. I want to look at the evidence and what the evidence suggests, and that would be true for a contested issue or topic like climate change. To From an uneducated perspective, it kind of makes sense that I put this much gasoline in my car. I still drive a gasoline-based vehicle, and then billions of people are doing the same thing every day. And we have a fairly large tank in our vehicles. If you're driving a four-wheeled vehicle, and all that fuel burns up and it goes up in the atmosphere. And common sense, if you just reason using like just common sense, then that carbon is going somewhere. It's going in the plants, the trees, and plants and trees and bacteria can only fix that much carbon or carbon dioxide. So where's the excess going? Is it remaining in the atmosphere? Is it mixing with the oceans? Or if there's 3 parts ocean, is it going to lakes and rivers? What's going on, right? So these are the kind of questions I think of when I think of parts per million, right? So that's what ppm stands for. And I spent a little bit of time looking at this. I've spent a little bit of time overall looking at this, and my first introduction to this from from more of a perspective of what can we potentially do about the climate, particularly the carbon dioxide problem. What can we do about the carbon dioxide problem? I started reading up on this around a decade ago. Not like I haven't been like this has not been a consistent theme. Depends how you look at it in my life. So I haven't been reading up on climate change in the books or periodicals, but I've kept a eye out for high-level data through NASA and other space agencies. And but yeah, anyways, going back to like what I can recall from memory, I think the first book I read on the topic of what can we do in terms of a geoengineering hack, that's how we were thinking about this, I guess, about a decade ago. I remember going through this book. I think I was, yeah, it's about a decade ago, roughly about. And I can't remember a lot of use cases from the book, but as I've documented in the notes, I do remember they were thinking about some pretty, well, it seems extreme to pump a lot of iron into the ocean so that the algae would grow around it and it would just sink to the bottom, to even things like injecting particles in the atmosphere or maybe the stratosphere in order to build the temperature down. And scientists discovered that there was a decrease in temperature when volcanoes would go off. So significant reduction in temperature that lasted for quite some time. And that's because the particles still were percolating somewhere in the atmosphere. So this is what got scientists to think about, what if we did that same thing in a controlled manner. So I don't know, like I haven't like exhausted this spectrum. Actually, I haven't even scraped the surface of this, so I am not in a position to be able to um, either lend support to or on the contrary to ideas like this. Um, I'm a lot more interested in getting to the truth of, first of all, what if there is a correlation. And I made a note here somewhere because I was going through these links. I think this, it opens up, if I click on this link here, the climate time machine by NASA, I think it opens up that link that was just open. But I'm just going to open this up right now. So if you go to the climate time machine by NASA, you can just Google it as well. Then there are 4 topics that NASA highlights. And I kind of went from right to left. So there's the global temperature data from the 1800s. So I guess this is based on just manual temperature readings that were being taken from a whole variety of sources, and somebody just geolocated this and made a dynamic because I doubt we had satellites in the 1800s. Maybe there were weather balloons, things like that. I'm not really sure how this data, what was collected. So as more time passes by, there seems to be an increase in global temperatures or global temperature. And this trend, if so, like again, it's like, what's the cause, right? If there's a correlation with CO2, rising levels of CO2, then if you don't do anything about that, then the trend would continue. And that would be pretty bad. And maybe I'm thinking about this right now because it was pretty hot yesterday and I was with my daughter. And I was concerned she would get a heat stroke, which, yeah, we should not have gone outside yesterday. But I've been thinking about water-related issues for quite some time. Okay, so the carbon dioxide. Now, this is data not from the past 150 plus years. I can't do the math of how much the range was for the previous visualization, but this was more on a 18, 19, 17-year time span. 19 years. Right. Now we're talking about the atmospheric carbon dioxide, which is the title of the video, I guess, I'm making. In this less than 20-year time span, actually this data is only for a period of 14 years, this 2002 to 2016. But even within this time frame, we are seeing an increase in carbon dioxide emissions. I wonder why the bands show up at the poles. Like why, like, is it has to do something with the spin, rotation, air currents? Or is it the fact that that's where the measurement instrument happened to be? I don't know what the reasons are. But as more time passes by, we're starting to see a lot more carbon dioxide in the atmosphere for pretty much all over the place, and not just the poles. I don't know, again, how the data is. Wow, it's definitely a lot more carbon now. It's going from like 300 and something range to 400 and something range. Maybe the instrumentation got better, right? That could be a correlation. Sea level rise, you can kind of focus on different areas. Like this is contingent on the assumption that there will be a complete melt of the Greenland ice sheet. And if that sheet melts, it will raise global water, sea level, sea level will rise globally by 5 to 7 meters. That is 16 to 23 feet. So this is for southern United States, southeastern United States. Northern Europe would look something like this. Amazon Delta would look like this. And Southeast Asia would look like this. I think that's Papua New Guinea. I could be wrong. That's Malaysia. That's Indonesia. That's Malaysia. So I don't know what country that is. That's parts of Australia. Bangladesh would like be hit. Like I feel like they should have put Bangladesh here because coastal flooding is always a problem there, as well as South Asia in general, because a lot of the regions where there's high density of population are actually at or below sea level, and rising sea levels are going to cause havoc in those places. And this is why I'm like a proponent of actually getting rid of nuclear, because a lot of nuclear power plants are built along the coastal area, which I think is going to be a huge problem if for some reason, with a statistical probability that something like that would happen over days or weeks or hours at that. But if it happens, or even weeks or months, if it happens over weeks or months, then we have a whole host of problems. But one of the core pressing problems right away is going to be nuclear. And I'm not a big fan of nuclear. I'm not saying we should scrap nuclear. I think we should keep it as a backup. Building nuclear power plants right next to the ocean just scares me. It scares me in general. Everything nuclear scares me, unless it's TerraPower, which is like been designed to replenish nuclear waste. Anyways, this is CIS extent. So it's from 1979 till pretty much recently. Let's run this again. Hold on, let me pause this. So data started collection. I don't know whether this data was collected 79 because Apollo mission being around for quite some time. So we should have at least satellites in orbit since the 60s. So I don't know. Anyways, I don't know where the data from the 60s is. That's an assumption that we were measuring polar ice caps since the 60s, when that may not be true. But this looks like definitely stretching from the northern end of Greenland. On the other side, you have Russia. I think you have the Nordic countries here. I don't know what this is. Okay, that's Iceland. And Svalbard. That's Svalbard here. And that's, well, obviously that's Russia here, right? Because that's like the Alaskan region. That's Russia. So it's extending quite a bit. You see the extent kind of range till here. It's like the 80s. But then it starts retreating quite a bit. So starting with the year 2000, it's a 20-year stretch. It's already retreated quite a bit. This is going to eyeball this. Depends how you measure this. Like what is the range? Is the art? What's the range? I think there's a way to do this officially. Like is it based on the hemispheres? Like the tropics is called the subtropics. It's based on something else. Like, like coordinates or something else. I don't know how this is really measured, but if I was going to eyeball this and not include the Greenland ice shelf and just kind of focus on the sea ice on top of the water, I think it's just water there. If the ice melted, there would just be water. I think I could be wrong. But if this region here represented 100%, and if I was going to eyeball this, but it's like all this other ice too, like between like this is northern Canada, and the passage is like opening up here, right? So this is north of Canada. This used to be all ice, and now it's opening up so that. But I would say like the extent has the sea ice extent has decreased, at least in the ocean part, like by maybe at least half of it is gone, if not 60, maybe 65%, maybe higher. Hard. I can't come up with it. Looks like more than half of it is gone because the extent is. Well, let's figure this out. So let's draw something around it, right? So let's see if this is what we're measuring, right? So I'm gonna try to eyeball this. It's not really scientific. This is really bad assumption. Okay, so this is 100%. It would be like here. This would be 100%. No, this one. Right? And what about these parts? Should we not measure them? Okay, well, let's just like say this is 100%, and we're gonna run this. We're just gonna fast forward this. So first we had 4 parts full, almost, and now it looks like this part could fit here, and this part could go here. So yeah, about 50% of the 50% seems to 50% reduction in a span of 40 plus years. 41 years exactly, because data collection from 2020. 50% reduction in 41 years, which again, if the correlation is increased level of carbon dioxide, then we still have the same inputs going into the system. So reasoning through analogy, I guess. I don't know if I'm reasoning by first principle. More population, more people moving into the urban hemisphere, and the same means of getting their energy would mean that the sea ice would be gone, right? The question is, what happens as a result of that? I don't know. I don't know when they say permafrost, what that really means. I guess I could Google that right now. I also don't know. They say there's a lot of permafrost, a lot of methane trapped into the Greenland ice shelf, which is going to be next, right? Because it seems unlikely that things will just stop once the ice shelf itself is gone. The other question is, what percentage of the sunlight is actually reflected back from the poles? And when you factor that into the equation, when all of that sunlight is now hitting Earth directly, it will raise the temperature up more, which means whatever ice is left in the Greenland shelf, elsewhere in the glaciers, is going to melt faster, which sounds like a whole, I don't want to use bad language because I'm not going to use bad language. Yeah, I'm not going to use that. But it just sounds like a lot of big problems. I'm not a climate scientist. Okay. Anyhow, okay. Well, so that image, I can't. Annotate. Right. So anyways, so yeah, that's the time machine from NASA. Again, I'm not a climate scientist, so I don't really know if there in these correlation leads to causation. I just thought about this, not an exhaustive list. I do believe or think that if we are wrong about the correlation, then that would be very problematic also, because well, if it's something else, if it's a Milankovitch cycle, which I don't understand about, maybe again it has to do with our relative position in the solar system, maybe it's a solar cycle of sorts, then we would have expended a lot of energy towards doing things which we may not necessarily. I still believe that the switch away from fossil fuel is something that's necessary for a whole variety of reasons, because it's a it's not an exhaust, it you cannot replenish it's a finite resource, so we're going to run out of fossil fuel soon. It's not 100 years, even if you can tap into the resources on Titan, you will run out of those resources. So we have to be very clear on the correlation, and we need to be really, really sure about that. And the other thing I mentioned is like this cognitive capital that we are investing towards solving the problem based on the correlation we're drawing. It would be better spent on enabling healthcare infrastructure, protecting the rainforest, and tackling other existential risks, and just making life better. But right now, it does look like there's a correlation. So anyways, I spent like an hour and a half looking into this. I started with just like simple Google searches about how like there's some debunking like the climate myth that there's only one station in the entire world, and it uh, takes the readings, right? So Mount what's it called? Mauna Loa in Hawaii. Um, but the truth is that there are many hundreds of stations spread all over the world, 66 countries in particular, and they have all been reporting the same statistics. There's a rising trend that has been observed, not for 10,000 years, but since we started taking these readings. So I think there was a switch around the 50s. I think it's right here. Past the 50s, it's the readings, but prior to the 50s, the mechanism for sampling ice cores was leveraged. Anyways, yeah, so, oh, I didn't read the comments, excuse me. Yeah, I didn't go through the comments. So those are the readings. I started looking a little bit into ice cores because I had some ideas of how this works, but I didn't really get into the details. So the ice cores are, I don't actually know where the ice cores are taken from, but I think it's in the polar, somewhere in the polar caps in Greenland, where you've had the accumulation of snow and ice for thousands of years. And this is a really good article. It's short, to the point, but it provides a high level overview of what we can actually learn from ice cores with the changing seasons, because you have dust and particles settling on layer by layer. And so when you drill deep down into the core, some of these can go down like to the ranges of, I think, kilometers. then depending on where you dig, you can have a view of what the climate has been throughout. Again, like I say, the time range, right? Um, and there's another article that I found. Um, this one. This one is really in depth. I really like this article. An introduction to ice cores from August 14, 2017. Um, so this ice core looks like it has a lot of bubbles, or it's kind of like flaky ice. So I wonder if it's more so from the top part of the core. My understanding, and here is a scientist actually digging a core manually. Um, I think now they have actual, anyways, drills. Yeah, this was more of my understanding of what an ice core would look like. It would be something a lot more compact because you have a lot of pressure, like kind of weighing down on that ice core for thousands of years. And I really like this image because the description is it's so rich. As you see on the screen, that there's a dark band in this ice core, and this was indicative of volcanic activity around 21,000 years ago. I wonder which volcano erupted at that time range, whether somewhere in Iceland or elsewhere, for it to deposit, which seems like a fair bit of sediment. Uh, I'm eyeballing it. I have no idea how big this core is. Judging by the size of the rack in the background and the left-hand side cabinet, this looks to be a couple of millimeters of a deposit for those volcanic ash. But yeah, I really like this image, and I like the article itself because it's a very in-depth primer on well, ice cores. And I learned a couple of new things after reading this article. Yeah, that's oldest one is around 800,000 years old, from the Antarctica, East Antarctica region. And the other thing is that scientists can and do merge the data that they observe from the ice cores with other geoinformatics or geomatics data, meaning data from satellites, radar. I'm thinking that's what geomatics means. But you can so yeah, I'm not going to be able to do a good job explaining that, but basically, there's a couple of different mechanisms through which you first measure what the ice core itself, and then you can correlate that data with other information. So it's not just the sediment. You can look at the bubbles inside of each slice of the core. So I didn't get into like a lot of detail of how, excuse me, how sorry about that, um, how the actual ppm value is actually derived. I wanted to get a little bit deeper into that because it says parts per million. So if I have now an ice core, and I'm like, so say, imagine, maybe I have a flask here, right? This is a bad example. Now imagine this represents the ice core. And if I slice it right here, right? And this slice is like, say, 10 centimeters, or sorry, like a centimeter wide, or maybe five millimeters of that. That's quite a variance. Say 10 millimeters, right? So what exactly am I looking for there? Am I looking at the bubbles? And when I look at the bubbles, can I tell that this bubble has X number of carbon molecules trapped in it versus other molecules? And then I just kind of go like, whoop, whoop, whoop. Am I running through some machine learning algorithm, or like what's like, am I doing an approximation? What are the set of routines that are activated or mechanisms? Because this is a scientific phenomena, right? anyone can conduct this experiment in order to validate or reject this hypothesis of X number of parts per million per core or slice of the core. If this is how it's actually done, I could be wrong. But I was trying to get into like details like that. I don't know if I, amongst all the other things, I may have missed that detail, but yeah, I was like really curious, like how is this measured? But anyway, so the article continues. I was really interested in how that works. If somebody knows that, please share that with me. The article continues on what happens with the ice core. So it looks like there's a ice core library of sorts. I don't know if it's called that, somewhere in Colorado, where the temperature is kept at minus 36 degrees centigrade, minus 32.8 degrees Fahrenheit at that. In order to be able to do core preservation, so scientists can send an inquiry to be able to have samples sampled from this place. And this seems like a treasure trove, because I wonder what kind of machine learning algorithms can be applied to these cores in a manner that is non-destructive, and that would be really interesting to find what AIs are going to find hidden in this data set. So yeah, anyways, really informative and descriptive article. If somebody's watching this, you might want to take a look at that article. Yeah, I think this was the core, like the gist of one of the gist that I captured my attention. So I'm going to read it. Additionally, as the ice compacts over time, tiny bubbles of the atmosphere, including greenhouse gases like carbon dioxide and methane, press inside the ice. These air pockets, fossils, provide samples of what the atmosphere was like when the layer of ice formed. The scientist said, scientists can directly measure the amount of greenhouse gases that were in the atmosphere at the time by sampling these bubbles. So yeah, again, going back to my comments, like, well, how does that really work, right? I'm looking at the bubble and I can tell X percentage of this greenhouse versus that, but how does it really work? Yeah, I'm just stating the obvious, the scientific method. You have a hypothesis, you conduct an experiment in order to validate or reject that hypothesis, which is what I'm trying to capture here. Which actually is a remarkable thing in this context, any context really, specific to ice cores, a team from anywhere can get together and they can go, I'm pretty much reading what I just typed there. They can go exactly to one of these sites, not too far off from there, because you're going to get different readings. If you're like 50 kilometers away, I'm thinking you might get different readings, maybe not. But you can conduct the same experiment or be able to, again, reject or affirm an hypothesis. So I've added some other screenshots. What are some of the problems that exist? I think it's this one. Oh, this is what I was talking about. The data is collated with other information. Folders, I think it's this one. This is an interesting screenshot, if I may. Same article that I was just sharing. It makes you think and ask more questions. I wish I could highlight this somehow and see, can I come back to this? Interesting. What's doing? Right? That's cool. That works. Oh, assign to anyone. No, we don't want to assign to anyone. I want to assign it to myself. Okay. And yeah, just kind of building up on that. What does stratigraphy mean? I mentioned merging data set. So in the decided act domain, now shifting to the actual idea, I'm going to draw some pictures and should really invest in a back home tablet. But I was thinking this could be made in Australia, right? So let's start with Australia. I'm going to try and draw Australia. Like that. Looks more like the head of a dinosaur than Australia, but let's just bear with me. That's Tasmania. I've always wanted to go to Tasmania. It sounds like there would be some like exotic plants and animals there. That's my understanding. Could be wrong. It just seems like a island that's cut off from the main continent. Anyhow, so imagine this is Australia, and imagine there's a part of Australia that is near the coast, but there's not a lot of population there, right? So now imagine this is a scaled version of that region, right? Just hear me out. And what we're trying to now do is sequester CO2. That's our intention. So for this idea to work, you conceptually need a couple of key ingredients. You need some engineered bacteria, and then you need water, then you need sunlight, and you need some kind of a container, right? So, so what would this look like, first of all? I don't know. I haven't run the numbers, but if I could, like, I'm not drawing this to scale. I'm not saying if you look at this whole region, you're going to see tens of thousands of these structures, right? So let's say you did do a test facility, and in this test facility, you make these earthen structures, literally taking the regolith from around you and making these 3D printed structures. So low cost, not a lot of capex. You pretty much just have to send one of the Icon 3D printers. I actually do not benefit from promoting Icon 3D. In terms of disclosure, I am connected to one of their investors, but like I've only sent them a message. They actually added me to their network. So, and just in terms of 100% radical honesty, maybe we will raise a round to the same investor in the future, but that is not why I'm promoting this. So it's not necessarily Icon 3D. It could be any company doing mass scale 3D printing. There's lots of company active in this space. In China and all over the world, in the US and Europe, everywhere, really. A lot of companies are active in this space. I think Icon 3D is doing a pretty good job. There's some other companies. There's actually one company, Winsun, I think it's called, from China, that I've reached out to. I never heard back from them. Right? Anyways, so you have now these containers pretty much made out of earth, right? With some other kind of technology. Now, how would they, like, what would be another view of this? So I've kind of shared some of these ideas I don't exactly know what they will really look like. But my main goal here is to protect the life form that's in the ocean, right? And I kind of envision that they are going to be in a lagoon somewhere where the water is shallow. So you can just 3D print these structures and hey, if it, if it, well, how much of the regolith do we actually want to have mixed with the seawater for when will it start becoming a problem, right? Well, maybe there is a solution to that as well, because instead of it corroding, you can just excavate it and take it and dump it somewhere here safely in the desert so that it just becomes regolith again. But anyway, so I don't know how this is actually gonna work, but I was thinking, um, and this is I'm not borrowing ideas from this one company that is already making these installations from in Middle East. But I don't know. I haven't figured. I haven't. I'm not gonna. I'm not even actually gonna spend time to solve somebody else's problem. Unless we're getting paid for it. But what I was thinking is some way of making this. Yeah, I don't know. I haven't thought about this. And so, but you then what you would have is you have the inlet of water. So you already have water coming in, right? And uh, and what you have is the how which color should I use to denote bacteria? I don't know if it's going to be algae or what it's going to look like, but then you have a lot of bacteria growing here because it's just going to be cellular division. 2 to 4, 4 to 6, 6 to 2 to 4, 4 to 8, 2 to 4, 4 to 8, and 64, kind of go from there, right? So if it's doubling, the growth is going to be exponential. So there's a back of the envelope calculation with regards to the dimensions you have and how long it would take for this amount of nutrients and sunlight to be provided and water for it to become this many bacteria. Okay, with me so far? So the first step is to engineer the bacteria that can do what I just shared. Actually, I didn't share that. It ingests the CO2, intakes the water, and then leverages photosynthesis in order to combine all of, well, do that process in order to make plastics that do not break. So this came as a news to me when I started thinking about these set of ideas again about 6 days ago. But today we have microbes that can do what I just shared. And now step 2 is what I'm doing here, right? Step 3 is getting the water to here. Step 4 is energy, right? So I crunched, I just did some numbers and then crunched numbers. So in terms of how much energy is going to be needed for bringing ppm back to pre-industrial levels. Okay, let me stop sharing for 1 second. And parts per million. I don't know if I mentioned this. I may have parts per million CO2. And we can start again. And I'm back. So yeah, I don't think I shared this image, but I think I put that in the notes somewhere at the top. So latest measurement based on NASA's website is 417 parts per million of carbon dioxide. And the high level data collected from 1958, the link's also right there. And when I manually did the subtraction in a period of 63 years and 7 months, parts per million have gone up by 102 almost. So that's in the 63 years of development, urbanization, human activity. I don't know what the delta looks like, what the rate of change looks like. And then I already kind of shared the other details. Now, if you're trying to visualize it, then where is my link again? Is it this one? This one? Too many tabs are open. I'm going to close some of my tabs. Where do you go? This one. Sorry. Sorry, just move it here. So I guess this is from that East Antarctica ice core study. But as you can see, these have been the readings for the past 800,000 years. I wonder why it does this, first of all. What's going on here? Right? And what does this mean? Like, does this mean, does this represent an ice age? Because they're saying warm period interglacial. So every time it's over like the 225 range, it's a warmer period, right? And if it's lower than 175, is that an ice age? I don't know the answer to that question. Somebody educate me on this. Yeah, these are troubling images of like we have already put enough carbon in the atmosphere. That's having an impact on crustaceans. That's an ocean snail, and that would be a healthy snail with smooth ridges around its shell. And now it's dissolving. So that means the acidity is higher in the oceans. There are abrasions, but does correlation lead to causation? What if it was scraped on the rock because of something was trying to eat it or something? But is this happening to a lot of snails is the question. I'm coming at a very uneducated perspective, so I'm hoping no climate scientist is gonna watch this and get this well, angry. There seems to be a correlation, more CO2 emissions and increased parts from which makes sense. Going back to my comments towards the beginning that only so much of the carbon dioxide can be fixed. But this is the main issue, right? This is the problem. Because I think there's a lot of information packed in just this one image. And if you slice and dice through this image with what this really means, then, oh, it's right here actually. How could I miss it? It says right here, ice age, glacial ice age. So if this represents an ice age, and if, let me try to, I'm gonna put some kind of marker here. Okay. If this represents an ice age, then the last one was not too long ago, because that is 200,000 years. That's 100,000 years here. So looks like the last ice age ended 20 maybe like 20 to 30,000 years ago. Because that's 100,000 years, right? That would be 50. That would be, yeah, 15 to like around 15,000. That kind of makes sense. It all makes sense because that's when the Sumerian civilization started. Now, it's not that Ice Age ended and civilization started. It would have taken a lot of attempts to start something like a civilization. But the thing is, fossilized record, I'm going a little off topic, but the fossilized record says that humans have been evolving for, well, it depends what you mean by that, but the brain has been evolving for 1 million to 2 million years. So between all of these ice ages, the human brain continued to develop. And there was all this mixing and matching happening between the different Neanderthals and humans and Denisovans. And the neocortex expanded almost double in size during this 1 million, 2 million years. But anyways, to come back to the thing, the data seems to be clear that we haven't pumped this much carbon dioxide in the atmosphere. We haven't seen this much carbon dioxide in the atmosphere ever. Based on, well, not ever, but like where ice cores go back, like I think the oldest ones again are 800,000 years, right? So, okay, so let's go back to the idea. And where's my picture? Oh, it's gone. Oh, well. Okay, so the numbers. So it's said that we need 1 year's worth of solar energy falling on Earth in order to bring ppm back to close to or at industrial levels. So let's go back to this image. And I'm not a climate scientist. My take on all of the things I say, particularly this topic, could be very wrong. In fact, I may be coming at this from a perspective which could be categorized as dangerous, bad information, right? Pseudoscience, even though that's not my intention, but I'm just putting that disclaimer out there, right? But let's think about this. Suppose everything that we need to do, if there is indeed a correlation and everything we need to do in order to bring ppm back, suppose we have those breakthroughs and we can bring ppm back in a safe way without hurting any creature, bacteria even, but nothing. Not even a single bacteria gets hurt as a consequence of bringing ppm down, right? Forget the insects and other organisms. Now, if you bring it back to, like, I don't know where pre-industrial is here. Let's see if we can find an image. Okay, so pre-industrial. So I'm looking at the axes on the vertical axes on the left. So it depends what you mean by pre-industrial. When did the Luddites, hold on, how do you measure that? Let me Google this. I'm not going to use Siri right now. I'm just going to Google it on my phone. I told Ryan that there may be a solution, and I think he was like, yeah, deal with her. I think it was around this time, 1750s. Okay. Well, 1811 to 1816. So yeah, plus minus 61 years, right? So this would be like the beginning, I guess, I would say, of the industrial age. This is when people started losing jobs that used to exist at that time. A lot of manual work, like tilling the soil and making a lot of things by hand, and factories started going up. So there was some discontentment, and this is where the Luddite movement happened, and it was crushed between, I think it was, forget what's time ranging. Oh, I closed the tab. It seems like 5 or 6 year time range. And then we have seen, well, let's say let's industrialization started like 1800, which is not like true. It started earlier, right? But let's say the factory started getting put in place like which is again not true. So 1800, right? And so during this time span of looks like 220 years, ppm has gone up from less than 280 parts per million to 417, right? It's doubled, right? 218, oh, no, not really. Less than double. Was 280, 560, right? Yeah, 560. So, well, it's appreciated quite a bit since the dawn of the industrial civilization. So again, a correlation is like, is it because, again, of human activity, or is it because a lot of volcanoes erupted, or I don't know, some things going on in the oceans? There's just more humans on Earth breathing up the oxygen and exhaling carbon dioxide, which would be human induced. But the main question is, what's the major contributor to the parts per million, right? Um, yeah, I haven't like looked at it. I'm sure there's data on this. Anyway, so let's go back to the idea. So the numbers. Okay, let's come back to the numbers. I don't know why I went off on that tangent. So 1 years of solar energy falling on Earth. Oh, yeah, this is why. In order to bring ppm back to close to or at industrial growth. So again, if we bring ppm back to, oh, that's really interesting. This is a dynamic graph. And I have no idea how to make it back. Go back. Oh, no. Are all these dynamic? No, just kind of like. Okay, so what was it? 1800? 1810 is around two, I'm eyeballing this, 270 parts per million. Ice age seems to happen around 170 parts per, 175, 170 parts per million. I'm eyeballing this. Although there is an ice age around this, oops, I don't know, like maybe this 180. Yeah, so I guess if it's going sub minus 250, then it could be a cause for concern, right? So anything lower than 250 is, or even 260, or maybe 265, or actually anything lower than 270. I don't know, right? So again, this is bad. This is a bad way of looking at this, but I'm just trying to understand like what's a good range. I'm sorry, I mean like these. I'm not sure about the ranges. I think is the right way of looking at this from an uneducated perspective, but I'm not sure of the ranges. So 275, right? So industrial started here, 275, like somewhere here, right? So naturally, we hit that range close to, actually a little bit more than that, 430,000 years ago. So I wonder what happened here. Like, did a bunch of volcanoes go off? Like, what happened, right? There seems to be a fair bit of carbon in the atmosphere. Then again, it's also cyclical. So the question is, what's going on here? Why is this cyclical? Has this been cyclical? Why do the ice ages happen, right? I don't know the question of that. I've thought about this. I've thought like maybe there's a mini black hole in the outer solar system. Maybe there's another planetary body that impacts the Milankovitch cycle somehow, causes these perturbations which cause the ice age. Maybe there are biological cycles uh, that some kind of bacterial growth keeps expanding, and for some reason it then collapses. When that collapse happens, there's a higher concentration of oxygen in the atmosphere versus carbon dioxide. I'm not sure about the third one. And all of these theories are just theories. But anyway, so this looks like this is bad. Sub 200 is bad. Even 240 is bad. Actually, 220, it could be problematic, right? And where we are right now is also problematic. So this is like a, maybe this is the nice sweet spot, 275 ppm, right? So just to keep that in mind. If we are running some machine, some construct, some invention, then it's brought it down. I've spoken too much about this, but it seems like an important topic from an energy perspective. Is if you bring it down too much, you're going to bring about an ice age. And if you don't bring it down, then there's a correlation between CO2, ppm, and temperature, then that's a problem. Okay, let's go back to the idea at this point. So in terms of the energy, the amount of energy that falls on Earth for an entire cycle for 1 year is 3.7 septillion joules. So let's take a look at the bigger numbers. So septillion is here. All right, 10 to the power 24, if I'm looking at this right. Now, each hour, about 430 quintillion joules of energy falls from the sun and hits the Earth. Quintillion. So let's take a look at quintillion. Ten to the power 18. Yeah, that makes sense. 430 with 18 zeros. Yeah, 430 quintillion, which makes sense. Yeah, 10 to the power 18. Yeah, I was thinking like 4 point something. No, that makes sense. It's 430 quintillion, right? So 430 quintillion joules of energy falling from the sun, hitting the entire Earth. And so the fact that one side of the Earth is facing the sun, and it's all like, imagine like that just one slice was facing I wonder how they measured that, because there's a rate of rotation, the 24-hour period, right? So yeah, there's a simple way of doing this, because you can say this much sunlight is falling on a tiny piece of earth, and then you take all the coordinates, you take a region, just like a slice, and you break it down into that chunk, and you multiply that number by the number that you gathered by measuring, like you could be a small solar panel. So you put the solar panels in the coordinates. So yeah, I think if I'm I'm thinking about this right. Okay, so that seems fairly straightforward, how they would do the math like that. Sources Business Insiders, I haven't verified this. So anyways, what I did next was I just did a simple calculation whereby I multiplied 8760, which is the number of hours in 1 year, by the 430 quintillion figure, right? So I just did this on Wolfram Alpha. So again, how many hours multiplied by 430, and okay. Now, going a little slowly here, my brain's slowing down. We've been making videos all day. Now, the total amount of energy that humans use in 1 year is 410 quintillion joules. So it's a little less than the amount of sun that hits the earth each hour. If that, like, so just to repeat, the amount of sunlight that falls on earth every hour, if we had some ability to be able to capture all that energy, that would be enough energy to power the entire civilization for one entire cycle around the sun, 1 year, 365 days. I sound like Neil deGrasse Tyson. But that's a really interesting, I found that a really interesting figure, that now we're not gonna have the Neil to be able to cover like this large tract of earth with solar panels or some other, like solar panels would do, right? Primarily as the primary source. Question of how do you store that energy too, which is another thing. I think Bill Gross has solved that problem. But yeah, 1 hour of sunlight falling on Earth there's enough power in there to power all civilization, all residential, commercial, vehicles, everything, all buildings for 1 entire year. Okay, so I did some math here. I divided 3.7 septillion, which is the amount of energy, again, we're going to need to bring ppm back, by 410 quintillion. I don't know if I did the math right here, because each hour has like that's how much energy we use in 1 year, right? So the number I came up with was 9,000, and considering the fact that 1 gigafactory can indeed power, 100 gigafactories can power civilization for an entire year. That's the number I was trying to get to. I was like, what's going to get us to like, this is the thing, right? 410 quintillion, all energy humans use in 1 year, right? So the 3.7 septillion number, I divided that by 3.7 septillion, I divided that by 4 quintillion. Just like yeah, septillion is a big number. Quintillion, I divided by a quintillion, and the number I came across was around 9,000, a little over 9,000. So we would need 9,000 gigafactories in order to sequester carbon dioxide back to around pre-industrial level. This is a huge thing. Like, I don't know what this really means. Like, there's the climate conversation is going to kick in now. if we should do it, and if we don't do it, what's going to happen? If we do it too much, like I was saying, like I shared this a couple of times, what's going to happen? If we bring it down to a certain range, what's going to happen? Um, it seems a little counterproductive if you sequester the carbon, but you're still pumping out fossil fuel and selling it and burning it. So I don't know, there's going to be a lot of ethical questions, technical, first of all. I don't know how you want to start. I would think the technical is the most important, because if you don't get the details right, and if you're wrong on the calculations, you're going to bring about a mini ice age. So obviously that's a problem. And if there's indeed a clear correlation and you don't do anything about it, then that's going to bring about rising temperature levels, which is going to cause a whole host of issues. Maybe crop failures on a massive scale. There's going to just be that could it just doesn't sound right. So yeah. So then there are the ethical questions with regards to how deeply integrated the world economy is with fossil fuel, and then there's the political question of how OPEC is going to react to the mere mention that we need to go towards complete zero fossil emissions. So that would require for the financial system to be redesigned, because the dollar is pegged to the cost of oil, the way I understand it. And a lot of people may not like that. I'm not talking about the Americans, I'm just talking about the world economy. But so these are going to be the many challenges are going to be posed with regards to the in random order, the moral, ethical, then the economic, just totally in random order, set of concerns. Lives are going to get disrupted as a result of that. A lot of people get their livelihood from fossil fuel. There are a lot of jobs here, millions of jobs, extraction, refinement, maintenance of the oil fields, and then refineries, supply chain. Last end of the supply chain would be gas stations, then the car manufacturers. Only Tesla is fully electric, and others are trying to adapt. But we'll see how. Tesla's patents are mostly in the public domain. But anyways, so but what looks like we're going to need 9,000 gigafactories to sequester the carbon. So I started looking into lithium. Then I was like, well, I don't know. Like, I was kind of coming across information that was like saying we have enough lithium. Some articles were saying we're going to run out of lithium at the current rate of productions for EVs and other demand for lithium-ion batteries. So I started thinking how much lithium there is in the solar system. The answer is we don't know. I don't know if we know, because we haven't mined or mapped the other planets in intricate details compared to Earth. So then I started looking at molten salt batteries, if that could be a potential energy repository for the invention that I'm thinking of. More recently, the breakthrough for fusion has come to news. I came up with a set of ideas about 6 days ago. I've been working like chipping away on these set of ideas, but the news for fusion came out like literally like in the past 24 hours, something like that. My source is Dr. Michio Kaku. So this is the Lawrence Rivermore, I think it's called. I don't even know what the facility is called. But the problem is that the reaction is not continuous. And but it's an interesting breakthrough nonetheless that, it just kind of makes me wonder how much energy is actually packed in really tiny particles. And it's quite remarkable that you can point beams at these particles and fuse them together. And uh, I don't think we have had a breakthrough like this before. Depends how you look at it, but I didn't look at the numbers, but uh, I didn't look at the numbers in regards to how much energy is going into this versus coming out. But again, the question is the question of continuous generation. So uh, I haven't like put actually Heliogen is there. If not, I said if not Gigafactory and molten salt, then I said how many installation via Heliogen we would require. I couldn't find an actual fact sheet on Heliogen, and that's I guess when I started thinking of fusion. Um, Actually, just today I recorded another segment for cleaner water, and this idea is probably right up there with the other set of crazy ideas. One of my crazy ideas is growing food on windmills. Uh, um, Actually, it doesn't seem like that unreal or whatever the word is, considering that I wanted the windmills to go at a slower pace so that they're not sucking in insects and bats and whatnot. And yeah, it depends how you look at it. Like if the thing can rotate at a slower speed and kind of not just do this, but also do this. So it look like it would rotate like this, but also do this and come down. Or hey, so that's I don't know, but there's a new idea actually. There's a bladeless windmill, and I think that's a fantastic idea. It just vibrates and it generates energy, and it doesn't destroy anything in its path. Uh, it's not sucking in anything. So it's just like a tree trunk standing right there, vibrating, and it's generating energy. Um, but yeah, the idea I had today for water. Hey, who knows? Maybe it's going to be possible. I thought of a hybrid half plant or half tree, half animal kind of a model. Primarily like get a lot of clean water. Uh, so we'll see what happens. It's a more of a contraption versus invention. But like it's going to be interesting to see how technology is going to evolve. Things like CRISPR and organ regeneration are going to evolve, and genetics in particular. So that maybe who knows? Maybe we could have a set of breakthroughs that would make an idea like that take roots. In this case, pun intended. So I hope you watched the other video that I made about these inventions. Yeah, it's my criticism of fusion. And finally, last but not the least, I was talking about the plastics and how they should be coated with a layer of material. So when it does degrade, which it probably will, based on erosion, wind, sand, friction against the sand, wind, sun, in particular, the weather elements is going to chip. Stuff's going to come off of its thing and go in the environment. So if you're creating any kind of mega structure out of plastic, it's probably going to slowly leach into the environment. Anyways, let's come back to the idea itself. So this is what I was thinking. The idea in a nutshell is, again, I drew the map of Australia, so I'm not going to do that again. Imagine you have these drums, right? And you have the ability to be able to 3D print a lot of these made out of regolith. And inside of these drums, you have bacteria growing. Bacteria, okay? I'm gonna make the text size bigger. I have no idea. I'm gonna go back to drawing. And so you have bacteria growing inside of it, okay? So the other things you need is water. So you want to build this thing next to a sea, uh, ideally a lagoon, because you don't want the waves to hit it. You want it to be in shallow water. So you want to, this, say if this is the coastline and that's the lagoon, you want to build these in the lagoon, right? So no problem with sunlight, it's falling anyways. So you need some ability to be able to provide it with power. So you want to build some kind of a sustainable power system. No fission, please. No gas, no gasoline. That would be counterproductive. So you need the ability to be able to have. You want to provide hydro to. Oops, something happened. Wait, is this still recording? Yeah. Okay. So you want to provide hydro to this thing. And the sun is not a problem. You want to, I wanted to draw stuff again. So, oh, again, okay, let's do this. So hydro is going to be there. There's a hydro line. Because there's the hydro is going to feed into, you're going to need a lot of hydro. So then obviously the sun is here or wherever it is happens to be, right? The sun is going to, you need the sun to do its thing, and the bacteria are going to need the sunlight. It doesn't want falling directly on the bacteria, right? And it's ingesting the water from the ocean. So the other set of ideas for water, the other video I made. If that idea cannot be made to work, we can just make, for this idea to take off, you can genetically modify fungi whereby they absorb water, which is in the air anyways, next to the lagoon, because there's a higher concentration of moisture next to the seashore. Or some kind of like invention can be made so that fungi are absorbing the water. And what then they do is they absorb the water and they release the excess water for for the bacteria to grow. Or this is an interesting idea. I just thought of this. Or there is a set of genes that control functions in plants like mangrove. So mangroves have this ability in the cellular structure of its roots, whereby it can take in salt water and it has the ability to then filter the water, and it intakes it through its root system and through its being. So there are two processes that control intake in the plants and trees. It's called, thanks to a shout out to Blue, a string of 5 numbers, who is one of my followers on YouTube. This comes from my source, but I learned about this through this individual who follows me on YouTube. That's what you call it. Let's see if I can change the color here. So there's two processes, xylem and phloem. These are actual processes in plants and trees that control the intake of nutrients to the root system with some kind of a, it has to be bound to a water molecule, is my understanding, because that's what happens when you water the plants. The plants take up water, but they're also taking up nutrients through the soil. Now, what happens in mangrove is what I just shared. And now, not all the salt gets filtered out. Some of it does seep through its being, its system. And what mangroves then do is they excrete or secrete the excess salt through its leaves, which I find just truly remarkable, right? So there must be a set of genes that are responsible for these functions. First, the set of genes that enable these, the roots of mangroves must be different on a cellular level. So we must find out what is this, what is this phenomena, right? For not just mangroves, but any kind of plant that adapts, has adapted to surviving in salt water, whether inside the salt water or the surface, like mangroves have roots going into the ground, but they are growing above the surface. Another adaptation for mangroves is that their roots kind of start. I don't know if they do a U-turn and they start popping out of the earth, but they're doing this because the tides. Uh, I made the previous video, so you can take a look at that. But yeah, what if the bacteria can be engineered to take in salt water and yeah, like wouldn't that be amazing, right? The problem is like because scale, right? So if you put all of these machines in one area, then let's think about the series of steps. If we just focus on one output, we're saying, well, hey, do this set of processes. Oh, I forgot the main gist of the idea. So then there's going to be some kind of a structure, right? Maybe there's a conveyor belt here or something. I don't know how this is really going to work. Maybe there are drones that are flying here. But what these are going to do, these are remember these are like they don't have to be circular, they can be any shape. But these are structures whereby there's a lot of bacteria here, right? So there would be some kind of a factory or modular unit here, right next to each one of these things. I haven't spoken to scientists on how this is going to work, but the idea is that because I don't know how the plastic is going to be manufactured. Is going to be pellet based or something else, right? If it's pellet based, then we need to extract those pellets because we don't want to have those pellets go into the ocean. If there's leakage from any one of these facilities, even if it's a little bit, it's gonna all that pollution is gonna go in the ocean. So that's a problem. Maybe we need to dig. If we dig an inlet through the ocean and the water comes in, then that water is going to bring in microscopic bacteria and other useful, sorry, naturally occurring life, microscopic life from the ocean into that inlet, which is what was my whole set of criticism against the kind of water filtration system that they're thinking of implementing in the Middle East that is supposedly going to get rid of desalination the way it exists. So anyhow, I don't know how this is going to work, but the idea in a nutshell is that through the combination of these facilities, I'm probably taking too much time. I'm getting tired now. And the other factors that have been mentioned, what these facilities are then going to do is they're going to make bricks out of made out of plastic, right? And my thought was, if it's not bricks, what if you don't have to make this structure like this? What if you could just tell the bacteria to make a structure and it would make a structure, and the structure we could then make like a launch loop, not necessarily one that goes 80 kilometers up in the atmosphere, because that's what the conceptual design of a large launch loop is. It's at least 80 kilometers high, and it's 2,000 kilometers long. So when you plot this on the map, you need to put it on a wider geographic body, which would be somewhere, I would think, I don't know, it would be probably somewhere in Russia, Mongolia, in random order, Kazakhstan, or somewhere on the Western Sahara, or Australia. I don't know if I mentioned Australia twice. It could also be somewhere in northern Canada. I don't know what kind of terrain would exist. Depends, right? Could be on the Antarctic if you can actually build structures that long and wide on the ice, right? But the physics is something, um, like something tells me the plastic, no matter how durable they may be, and they may be reinforced with other materials, based on my rudimentary understanding of material science, current state, no material exists that would be in a capacity to be able to sustain a structure that tall. Even if you could extend the range of some of the tallest peaks on the planet by maybe a kilometer, 2 kilometers, it would still, I think, be in the range of less than 15 kilometers high. So somehow you dig a bore a tunnel through some of these mountains, and you then extend the range. Somehow that would still fall way short of the 80 kilometers. And hypotheticals, like if you just kind of like if you indeed build some kind of structure that is that long, it's not going to work. So what is the small one? I don't know. There's only one page for launch loop. Anyway, so let's go back to the idea. The idea in a nutshell, again, is pretty simple. Um, there's only a couple of core components to it. Um, the key ingredients are the genetically engineered creatures that are going to take in water, energy from two different sources, and sunlight, and the other energy would just be sunlight if it's a heliogen installation. I don't know how many we're going to need. I have a set of ideas to make heliogen sustainable, more sustainable. I don't know anyone there. But yeah, water, energy, carbon dioxide, which is, we have lots of it in the atmosphere, and some kind of a facility to house these beings. There's a containment issue here as well. I don't know how that's going to be worked through. Um, Maybe you have a layer of some kind of material around the edge or the rim of these vessels, that if the bacteria, the moment they get out, they just kind of get zapped or something happens. Um, and maybe they have a life, right? They come with a timer so that they don't go out and kind of proliferate in the environment. Uh, we definitely don't want a runaway reaction for this one. Uh, we don't want to, like, we want to have a very controlled environment, because we don't want this thing to go crazy and just keep making plastic. That would be pretty bad. Uh, yeah. Anyhow, anyhow, I don't know the validity of this idea. I just thought of this idea because parts per million is a has been a challenge, and I was thinking, if there is indeed a technology that can solve this problem, then the way I see it, the functional steps that stand in the way of getting to the kind of numbers we want to get to is, at least this is my second actually attempt at trying to put the pieces together, and I've been working on the water set of problems. For some reason, I don't know, keep working on it. Um, yeah, yeah. May common sense prevail. Maybe I think we need to invest a lot more time. I think my criticism. This is going off all off top. I gotta take a bio break, so I gotta end this video. Uh, Many years ago, I like made a comment looking at the trends about the automation and its impact on the workforce going back 2015ish actually. I forget what the Oxford report came out, but I was at that time critical of this whole creating jobs for the purpose of um, like however we sustain the I think we created a lot of fake jobs and it's having an impact on the ecology. Uh, I do have to balance those thoughts with the reality that if we create, if not do, but if we create an incentive or economic structure whereby um, there's less opportunities because we're saying, oh, if we create more jobs, there's going to be a lot more like PPT, PPM, or like whatnot. That's going to be a big problem. And that could have a lot of like that would make a lot of that would enable that not enable that would create a lot of human suffering. And it really sucks when the economic prospects are like that would not be a good reality, right? So I my personal thought is that humans should be incentivized to solve these bigger problems. And I think we need a new framework for that to happen. I don't think this is in the domains of the government. I would be shocked if any government in the world has a robust plan for climate change that they say if we execute this plan, then climate change is going to be tackled. I would be shocked. Or even a plan for managing the economy at that, right? I'm not talking about like steps to AGI or like like this. So I'm just yeah. Anyways, these are my thoughts. But this idea I figured I'd share it because it'd be cool if somebody built this. If nobody was going to build it, we'll build it. We'll build it. We will build this. We will test this at the very least. And we're going to need a lot of support because as with anything, there are promise and perils. So this would have to be done in a controlled, tested environment with yeah, the security aspect has to be considered for everything. So what I'm not sure about is a good idea because if you cannot coat that plastic in some layer whereby it's going to be, we can say, hey, this is going to be safe for the next 100,000 years in this time, in this temperature range. If the temperature is like past 100 degrees Celsius, then, excuse me, we have probably have other problems, like bigger problems. But if it can easily withstand temperatures of that range, I don't know where you'd have to encase the whole thing in. Just make it like a series of giant pyramids, maybe, and then kind of spread them out, or like a cluster of smaller pyramids, maybe the size of Sphinx, or the pyramids of Giza, and spread them out. Uh, the question is, if you put too much weight on one part of the Earth's crust, I know you gotta like it sounds a little like far-fetched, but you got to think about this, like, because I don't know what kind of weight are we talking about, right? Because they talk about gigatons, but how much is that when you sequester it, and how much will it be when you just the same thing twice? What was that? But yeah, I don't know how thick the crust is in one part versus the other, so we probably don't want to sequester all of it in one spot, or maybe we do. Maybe there's an ice shelf. Sorry, there's a rock that is really stable. So we break, or maybe just bury it, right? We dig the whole thing, run the diggers using fossil fuel and uh, solar, and just dig the thing and bury the stuff. Just bury the plastic. You don't have to make something out of it. Although it'd be really cool if you had a mini launch loop. It would help bring the cost down substantially, which is the indicator that we're really looking to push or incentivize if we can somehow. Anyways, these are my set of thoughts on sequestering CO2. You're welcome to do what you want with this idea. If you make something out of it, please think about me and my teammate because we spend a lot of time looking at trends like this. It takes a lot of our time, energy to break apart information, absorb information, mix and match it with what we know. And I think we should be compensated with regards to the good ideas we're putting out in the system. We also uh, maybe help out in some way with brainstorming ideas, prototyping inventions. So we're open to opportunities like that. We are adept at the ideation and prototyping on the mechanical engineering side of things. So yeah, the video became a little longer, but the gist of the idea is really simple. Can probably be encapsulated in this really badly drawn image. The only thing missing here is like a pyramid. So yeah, you want to build like some kind of a structure like this. Oh, okay. How do you build it? I don't know what that lion looks like. Is that a lion? No, that's a human that looks like a lion.